Hey, hello everyone. I'm Chiara Moretti. I'm a postdoc at the Observatory of Trieste. Thank you so much for inviting me. Today I will talk about how to measure evolving dark energy without prior volume effects. And this is based on a paper that we put out roughly a week ago with Maria Cedric and Pedro Carrillo. And this is actually two papers in one, because what we do is we propose a possible way of avoiding prior volume effects, but we also provide constraints on evolving dark energy that are based on LSS-only probes. All right, so what are prior volume effects and why do we want to avoid them? So just to set the stage, I'm talking about the standard way of doing inference with the summary statistics. I will focus on the power spectrum, so two-point function statistics. And what we do is we want to sample our posterior distribution in the space of nuisance and cosmological parameters to get constraints on cosmology. So once we sampled our distribution, what we do is we want to marginalize over the nuisance parameters because we don't really care about them. And in an ideal world, this posterior is a multivariate Gaussian, so we can just marginalize over the nuisance parameters and we get very nice Gaussian marginalized 1D posteriors from which we can get our best fits for the cosmological parameters. However, what happens often is that we have a lot of degeneracies between the parameters and specifically between the nuisance parameters for the power spectrum, as I will show you in a bit. So what happens to the posterior distribution if it has a weird shape because of these degeneracies is that when you marginalize over the nuisance parameters, you get shifts in the peak of the posteriors for the cosmological parameters, as you can see here. And this is due to volume in the prior of these nuisance parameters because they are not very well constrained by the data. And so this results in actually an impossibility of getting what you want, which is the best fits for the cosmological parameters. So as I mentioned, I'm focusing on the power spectrum and what has become kind of the standard way of doing a full shape analysis of the power spectrum, which is based on the EFTofLSS model. The model for the power spectrum looks like this. It has several contributions. It has a part that is based on standard perturbation theory that encodes nonlinear evolution, but it also has a contribution that comes from counterterms that include our ignorance on small-scale physics, and then there's also some stochastic contribution of noise. So this model, as I said, has become kind of the standard. It was used to reanalyze BOSS data. It was used for DESY, and it will also be used by Euclid. But the problem is that this model, when you include bias parameters, counterterms, and noise, has 11 nuisance parameters, plus the cosmology, which is what you actually care about. And these nuisance parameters and the cosmological ones are very degenerate, and it's very hard to constrain them. And in fact, when one does this analysis specifically for beyond ΛCDM models, so if one wants to measure say evolving dark energy, then you get these projection effects or prior volume effects that I mentioned. So for example, here is an example of what you get. These are 1D marginalized posteriors for the cosmological parameters that we get from real BOSS data, but we also show synthetic data in orange. So here we generate the data with the same model that we use to fit them. We should get perfect best fits. But what you get, if you focus on these two panels, W0 and WA, are very shifted posteriors with respect to the fiducial value, which is what is shown here by the vertical lines. And this is exactly what I was talking about before. Now, this is not news, and it was explored in quite a few papers for BOSS data, but this was also an issue for DESY DR1 full shape. As you can see here, the empty dots are the maximum a posteriori for these three parameters, while these filled dots are the mean of the posteriors. And you see that they are very different. and they only converge to the same values when you include CMB information and supernova information. So what to do? How do we solve this? Because the goal of stage 4 surveys is to measure beyond-ΛCDM, evolving dark energy, or dark energy in general. Well, the reason that we have these prior volume effects is that the data are not constraining enough. So one way would be to get more constraining data or combining with other probes, as was done by DESY, as I just showed. But another way is to change the priors, right? So again, this is because the shifts arise from volume in the prior space from parameters that are not well constrained. So one way is to use Jeffreys priors, uninformative Jeffreys priors. Another way that has been explored is to use HOD-infer priors, or, and this is what we propose, you could re-parameterize your model and see if there is some combinations of parameters that you can better constrain. So in order to better understand how we chose our parameterization, I'm going to do the next bit on the blackboard. Okay, so I showed you the model, but another way that the power spectrum model can be written is you can write your multiples as a sum of a non-marginalized part plus a sum of nuisance parameters times a marginalized part. So what do I mean by non-marginalized and marginalized? This is because a lot of the nuisance parameters that enter the model are linear, and this means that if you have a Gaussian likelihood, you can marginalize them over analytically. It's just a Gaussian integral. So if you write the model in this way, you can perform analytic marginalization, and so your chi-square will be composed by two terms. So the marginalized chi-square will be for the cosmological and non-marginalized parameters and non-marginalized parameters and the marginalized parameters will be a sum of two contributions. Yes, sorry. Better. All right. I hope you can see this, but it's okay if you can't. So the marginalized chi-square is a sum of two contributions. This part is called the profile likelihood term, and this is called the Laplace term. And this comes from the marginalized parameters. So this matrix here can be written as the contraction of the marginalized terms times the covariance okay? And this part here is exactly responsible for the shifts in the posteriors that you see. So to understand how to re-parameterize the model or to understand what are the best constrained parameters of the model, we can look at these terms. And for example, if I focus on the counter terms, these can be written as a counter term times a squared times the linear power spectrum. But actually here you also have the primordial amplitude. So if you want to write this as some scale-independent parameter times a function of k, so a scale-dependent part, what you're constraining here is actually the counter term times the primordial amplitude AS. And so this basically motivates our choice of reparameterizations for the model. So if you write the infinitesimal posterior distribution for these parameters, you will have times DAS times the likelihood. And if I change variables to this, then I will have beta over AS, AS times the likelihood. All right, so basically imposing a flat prior, which I think is an informative on the counter terms, results in imposing an informative prior on AS. And so to maximize the likelihood or to minimize the chi-square, what you have to do is to minimize AS, and this induces a shift in your posterior. So what we chose to do, well, it's not only AS actually that enters in the power spectrum, but there's also another amplitude because of the Kopachinski effect. Yes. And so what we chose to do is to constrain this alpha parameter that is the counter term times AS and this Kopachinski amplitude. So this is just a summary of what I just wrote. And this is an illustrative plot that shows you the different contributions for the profile likelihood term and this Laplacian term. And as you can see, while the profile likelihood is exactly centered on the best fits or input parameters in this case, because this is synthetic data, this Laplacian term has actually a weird shape, and it drives the posterior towards high value of H and low value of W0. But if we absorb the amplitudes, then this becomes roughly independent. And our posterior will be shifted back to basically this one. Right, so what do we do to understand if this works? So, as I said, we use synthetic data. So in this very busy plot, you can focus on the blue solid lines. These are the baseline approach, so without re-parameterization, and you see that they are very much shifted from the fiducials. It's also visible here in these 1D plots. And then we test different ways of absorbing these amplitudes into the parameters, and as you can see, these all work pretty well. In the end, what we think is the best is this pink one here, where we include the Kopachinski amplitude and sigma h square in the parameters. And just for comparison, we also show the results with Jeffreys priors, which is the dashed lines, and they kind of agree with our re-parameterization choice. We also do something similar for DESY-like setup, that's in the paper. But the last thing I want to say is constraints from stage 3 data. So once we have this kind of re-parameterization, what we do is we redo the BOSS analysis. And just for comparison here, we are also plotting the DESY, I think this is DR2, yes, DR2 data. And this is obtained in combination, again, with CMB data and supernovae. Okay, so if we only use BOSS, full shape plus BAO post-reconstruction, this is what we get. As you see now, this is centered on lambda-CDM. These are real data. We include also some external BAOs, both lower and higher redshift. This is all pre-DESY, so we don't include any stage 4 information. It's shrinking. And then we also do a combination with photometric data using DES Y3, 3 times 2 point. And that's the green one here. As you can see, it's still pretty broad and still consistent with lambda-CDM, but it seems to converge towards the same area that was obtained by DESY DR2. And again, this is an LSS-only driven constraint. So my conclusions. This simple, very simple and intuitive re-parameterization can resolve most of the prior volume effects, specifically when one wants to measure evolving dark energy. It's similar to Jeffreys priors because it removes the dependency on cosmology of this term here. But it's more intuitive if you know the theoretical model. It's straightforward to extend to nonlinear parameters, so those parameters that are non-marginalized analytically. And it's independent of the experiment because for Jeffreys priors, you would need to include the covariance. So in that sense, they depend on the experiment. We also produce constraints on evolving dark energy from LSS-only probes, combining spectroscopic and photometric stage 3 information. And these are the numbers we get. Still consistent with ΛCDM, but seems to be shifting towards what DESY found. So what's next? We are now looking at higher order statistics. And what I think will be very exciting will be applying this to stage 4 surveys, so DESY and Euclid. And a question for you all is how will this hold up compared to alternative methods? Because as we saw, the constraints are not that tight, so it would be interesting to see how it compares.